Okay, can you see my screen now? Hopefully the text is a little bit bigger.
Yes. Yes, very good.
Okay. All right. So this is kind of the basic FlexSim interface. You have a toolbar on the top, some menus, and then you have a library of objects that you can drag into your model.
Okay.
And then you have a toolbox, which is these are the set of kind of specific tools, like data tools. Sometimes in here you'll put like global tables, which are like spreadsheets that you can retrieve data from, etc. So I'm going to start out with just the library, and I just want to kind of show you, give you an intro to just the basic user interface of FlexSim.
Okay.
So you drag objects out into your model, and I'm going to create a very simple, what we call this a post office model, which is just parts arrive, they go into a queue, and from the queue, they are then processed by a process, some type of a machine, or this could be, when we say post office, a person walks into a post office, there's a person at the table, and it takes a certain amount of time to serve that customer. And then once they are done, then the customer leaves. In this case, it's just boxes going through, and the processor is actually a machine. And then you have things queuing up as as they arrive, they queue up, and then they're served by the processor, right? So this is, the visualization in this case is a machine that's processing stuff, but technically, it's very similar to people walking into a store. There's lots of different processes that this could be. I can also do very easy things like I can move all of these objects together. And if I say I want, if I'm in a factory and I need some transportation, I can drag out something like an operator. I connect this queue up to the operator. And then on the queue, in its properties, I check a box that says, I want to use a transport to send my items to this processor, and then you specify a reference, and that's this connector reference, which is a center port connection to the operator. And when that happens, when you check that box, you have an operator, going and picking up the boxes and transporting them to the processor.
Okay.
We also have things like conveyor systems that you can do. So you can drop out a conveyor, and I can connect up, delete that connection, and connect to the conveyor, and connect from the conveyor here. And for example, if I move this down here, then you'll have the same thing happen. There will be an operator that picks a box it up. He'll bring it over to this conveyor. It will convey over to the processor. And things will also queue up at the conveyor. So we have conveyor systems as well. Now, for your specific scenario where you're talking about trains, what we have is an AGV module. An AGV is for automated, what we call automated guided vehicles. We implemented this initially for, kind of autonomous robots that travel in a factory and move parts. But then as we expanded the functionality, we realized that this AGV could be expanded to simulate train motion, right? And so just to give you the interface for kind of how you build out these paths, so you have down here under AGV, you have a straight path, a curved path. You can join paths together. This is like a tool. And then you have control points, which are like points that you place on your path, and then they become destinations that you want to travel to. So I can create like in this case, I can create a loop. I'm just gonna create a loop of paths. And then I'm going to join those paths together with curved paths. So I click here, and that creates a joint between, like a curved path between those two paths.
Okay.
So I've kind of created a loop here, and then I'm going to drop a control point right here and a control point right here. And I'm going to use that source object again that creates these parts. I'm going to put it into a queue. And then I'm going to have a sink over here. And so I'm going to connect this source up to this queue, and then connect the queue up to the sink in the same way that I did previously. Remember how I created these connections that say, you know, parts flow from here to here and then to here, and then using that same mechanism, instead of an operator, I can drop out what we call a task executor, and that's like a little robot, a mobile robot. And I connect him up, or an AGV. I connect him to this little control point that kind of says, this is your kind of home station. And then I also connect this queue to this station, to this control point that says, if I want to go to that queue, then I should go to that control point. And for this sink, I connect this control point up to this sink that says, if I need to go to the sink, then I go to that control point. And then my final connection is, again, I do this center connection to the task executor that says, I want him to be the one to carry things. And then in the queue, I check this box, use transport. And by doing that, I can then I've created a kind of routing system where this task executor, or AGV, will pick up boxes over here. He'll travel on this path to this location, and he'll drop them off at that sink, right?
Okay. So now that gives me, that kind of starts to, in a certain way, that's in a good spot. So when I'm looking at a hump yard, though, there's a lot of back and forth motion. I would almost look at it as being like a mail sorter, because individual car will have what the hump yard does, and I'm sure you're familiar with. So apologize if I'm.
Well, I'll show. So. I've built a hump yard, and I'll show it to you later on. So
okay, yeah, all right, I just wanted to make sure that, because one of the things
I'm just kind of giving you the basics of how this, how how our FlexSim is structured.
Okay.
The other thing that before I just move on, the other thing that I could do on this guy, instead of loading them on top, I can have these loads be as, if I go in here, there's some settings that you can specify on this AGV network, where you can say for a certain type of AGV, I can attach loads as a trailer. And that means it kind of, instead of loading them on top of the AGV, the loads, whatever it loads on, it's like it hitches them onto the back side of the AGV. And so if you do that, and that's kind of similar to kind of how a train would work, right?
Yes.
So then when he loads it on, instead of being kind of on here, it's back behind, and then he pulls it. And this was kind of the initial, in the very first version of our AGV, we added this mechanism. And then over time, we've realized, you know what, we can expand that to do even more like sophisticated, like train simulations, because we can kind of do, because this functionality has this idea of kind of articulated motion, where it's, they're kind of going around curves in a way where it's kind of articulated like a train would be.
Right.
And so we've just, over the years, we've kind of expanded upon that. Okay, so now this is that I've kind of shown you the basic interface for how you build models in FlexSim. So I will open that model that I've been working on. So I just have been working on it, trying to get it running today. It's not perfect, let's see, where was it? Sample. So this is my hump yard.
Okay.
I've divided it into 3 areas. So we have, this is the, I guess, receiving area where inbound trains would come and be parked.
Okay.
And then this would be the hump. Now I don't actually put a Z lift in that area, but you could if you wanted to, you know, where you actually, where it lifts, it elevates above ground a certain amount. I did not do that, but you could certainly do that. And then this would be the classification area where you're sorting the various cars into their destination areas. And then this would be a departure area where once trains have been composed, departure trains have been composed, you come and park them in this area before they are routed out.
Okay, that's akin to what we consider arrival and departure tracks, and usually the arrival and departure tracks are right next to each other. But this is
okay.
This, I mean, it's not a big deal. If this is the way it works, that's fantastic.
Yeah.
So that's
so I'm reset. I reset and run the model. I have these trains come in, and I've kind of, as I've built the trains, I've colored the cars based upon the destination the destination train that they're going to go to. So these 3 will end up on the same destination train. These yellow ones will end up on the same destination train, etc.
okay.
Right,
so now, and sometimes.
But I guess I've just done it randomly. Obviously, in a real life model, you would do actual, perhaps real data that's saying this is how this train is made up. But go ahead. What was your question?
No, I was going to say, and sometimes it works in a different couple ways. Like, for example, you have those 3 blue cars together. Now, on a hump yard, the newer ones, now this isn't, you know, back in the past, they didn't have it, but they actually have, you know, the controller, and the train is being, as it goes by, it's going by an AEI reader, so it knows what car is there. And if these 3 cars go into the same location, they'll actually hump all 3 at the same time to that destination. So they won't run as individual cars, they'll run as those 3 cars.
Yeah, and I've done it I've made it that way so that when they're split off, it'll actually split all 3 of them together.
Okay,
right.
Good.
So then it'll come in, and this is the main engine, and then I have what I call a shunt engine. I'm not sure exactly if that's what you call it, but so this is kind of like the internal guy who pushes stuff around. So the main engine comes in, he parks these guys in one of these arrival lanes, and then I have a second one. I also have not, I haven't like tweaked, like there's going to be some overlapping at this point because I haven't done kind of mutual exclusion mechanisms where I say, you know, you're not allowed to go here when these other guys are here. But that's certainly stuff that can be added.
Okay. Yeah.
So these guys pull out. Once they've pulled out, then this shunting engine is going to come in and push them up the hump. And I essentially just specified, like, this is the point at which the things are then dispatched off. So he'll push them to that point. Unfortunately, they stop. Right now, it will only allow you to decouple cars when it's stopped. I know in some cases it'll actually decouple them as it's moving, but this one it stops, and then it will shunt this or allow this guy to come down the hump, and he will be dispatched to one or more of these, or one of these lanes. And if you look at a chain, so I've got a chain of 2 here. And it'll do both of those 2 at the same time. It looked like it did that one and then those 2, and that's because my randomness, I think, just happened to do 2 blues at the same time. So that's a tweak that I would need to make, but it's certainly, certainly something it's just various tweaks that I need to make to fix those little issues. But usually by default, when it has a chain of multiple, it dispatches all of them together. So.
Okay.
And so then they're then queued up in this classification area. So there we've got, 1 of 3, and then we get 1 of 2, and then it looks like it did 2 and then 4 on that one, but yeah.
Well, I mean, in the end, what becomes a bit critical on this part, and I'll have a couple of questions regarding this a little bit later on, but the key is the time factor and how long it takes for the cars to get, sorted, and stuff like that. So that there becomes the kind of our key factor. I mean, from what I'm viewing, this is kind of pretty much exactly what we want. The thing.
So on the speed side, hey, just a minute. Okay, sorry about that.
Okay.
So on the speed side, if you go into your AGV network, the way that we specify speeds is through there are different types of AGVs that you can specify, and you can have as many as you want. So you go over here and specify different types of AGVs. And then each one of those has kind of a speed profile. And it's broken out by what we call load types. And these are really just states of the AGV. And an AGV in this case is a train, right?
Right.
So it's split out by load types, and you can specify the set of load types that there are. So right now we have empty and loaded, but you can essentially specify as many columns as you want. And then at the beginning of every travel operation, which is a certain destination that you go to, it will decide based upon, I guess you get to decide which load type that train is currently going to use, right, for that travel operation. And under that, when in that travel operation, you have an acceleration and deceleration value, and then you have forward speed and reverse speed. I don't know that forward and reverse speed are going to necessarily be critical for you, but this would be so that you probably set them to be the same.
Right.
But then you have a maximum speed for every what we call path class. And again, this is configurable. So right now we have 3 path classes, which are straight, curved, and spur.
Mm-hmm.
And these path classes, again, you can specify that list. It's this list up here, and you can add and remove from that list of path classes. And then each one of your paths in your model, you can specify which path class that belongs to. So if I click on this guy and I say, I can click over here on path class and I get that option, right?
Okay,
over
right.
here. So if I say, even though this is a straight, path, technically a straight path, I can make him part of the curved path class, which means that when it resolves the speeds, it will use this row, and then it will use whichever column you have decided you know, to use for that load type for a given travel operation, right?
Okay. So in that regards, based on your paths that you have, for example, like when I use RTC, I have a whole bunch of what we call links, which is the same thing as your path essentially.
Yeah.
Then we have nodes, which become change points. And within a given class, I can assign. So let's say I have a train that's going on a main line that's 10 miles long, and it's subdivided into 2-mile segments.
Yeah.
Even though they're all main tracks, each segment can be assigned a different speed, even though it's the same class of track. So where you have, for example, you had the main line or the spur and the curve, well, it's all over the place. My curves may vary. So would I assign curve?
Yeah, what you could do is you could say, you know, you could say like, maybe I have main line 1, and then, or maybe I have like, main line fast, right? And then I have main line slow, right?
Right.
Right. And then, let me get rid of that guy. And so I could have, you know, I could get rid of all of these. If you don't want to do straight, curved, and spur, you can define your different path classes however you want. And then in your model, you know, you can split these things up. You know, it's for a given, I'm going to go create, you know, if I have a really long set, right, but I want to, you know, say, well, this section I want to be slow, mainline slow, and this section I want to be mainline fast, then you would split it into 2 paths, right? So you'd have one right here, and then one right there, and then you'd say this guy gets the path class mainline fast, and this one gets the path class mainline slow, right?
Okay. So, but essentially, a speed for a given path class is constant. So I would have to define, if I had 10 different speeds, I'd have to define 10 different mainline class paths.
Yeah.
Okay.
Yeah.
Okay.
And
well, I mean, it's not constant in as much as there's accelerations and decelerations at the beginning of the move and the end of the move.
Right, and that brings a, you know, and my guess is no, because I don't think any of the other ones do it either. But for example, in my RTC software, it's physics based, so there's algorithms for acceleration, deceleration based on the locomotive's tractive effort curve and then the weight behind it, and stuff like that.
Oh, yeah.
It does calculations across the thing, and my guess is that the software doesn't do physics-based modeling. I guess is the easiest way to do it. So we have to make sure that we were defined how the
close, at least try to get it close to where, you know, what the physics-based one would do, because ours is more simplistic, where it essentially, when it's on a given line, it will go up to the maximum speed of that line based upon your current load type, right? And then if it's about to go onto a slower line, the one thing important to note is it actually decelerates before it gets to that slower speed, so that it will still be going the correct speed on that when it enters that line.
That's the same pretty much the way ours is. I mean, we have the RTC model I use, it has similar parameters, and a lot of it is based on signaling. Some signals you have to be at a speed before you pass it. Some signals you pass this train and then you reduce to the prescribed speed. So there's variations in that, how that works. But in the yard, we're not going to be using signaling. Now, but to bear in mind though, that one of the questions we we had in our list there was if you can model signaling systems, because what the goal here is, and from what I'm seeing, this is really good. We need to be able to model mainline tracks adjacent to the yard or classification yard. We'll have trains coming in and out, the arrival and departure. We have to make sure that the trains are governed by something that is realistic to how. In other words, if I've got two opposing trains, let's say we have two tracks, and we have two trains approaching each other on the same track. Well, obviously, we want them to stop and one signal and to make it, and it'll cross over to the other track. And then when the path is clear and the signal is cleared up, then it will move. So that signaling systems for the hump yard itself is not an issue. But what we're trying to do, we may be trying to do on the other stuff is to at least get something similar as trains enter and exit the yard. And that's where it becomes kind of crucial. We can do some of that modeling outside of this and then replicate it based on how you're showing here to a degree, but it's easier if of course, the RTC software is a smart software, so it really dispatches and itself. And I can show you a sample of how that works in a little bit. But from what I'm seeing so far is right. It's just that I want to make sure that we can replicate, and it goes back to being the time. How long is it taking us to do this? So we can replicate speeds that are, and obviously it appears we can, that are appropriate to what's happening in the yard. We know and see the capacity if we bring X amount of trains in. I mean, there's a lot of variables that we're thinking about how to attack it, but the one thing we need to make sure is that it does reflect realism. And of course, so far what I'm seeing, it does.
I think so we should be honest, like at FlexSim, like the consulting department at FlexSim internally, we have not yet done a train yard simulation, but some of our customers have. We do have customers who have done very sophisticated train yard simulations. And so it has been done. Unfortunately, like I feel like I can say, yes, you can do very well configured speed configurations, to make sure that things are going the speeds that you need them to. But as far as the experience goes, perhaps we should connect you with some of the people who have actually done simulations and, in train yards.
Well, I think at this point in time, and that's fine. At this point in time, though, I think what I need to make sure that I'm following is that how are the capabilities of what it is and how we can use it to do it. So the signaling part, well, the important part about that is to actually prevent, like I said, if we have two trains running in opposite directions on the same track and there has to be some sort of move, and part of what we would be doing, and that brings it to another point, and I'm kind of going off on a tangent, so I apologize. But we'll get situations. Well, what if we have contingency? What if X train arrives 10 minutes later than it did previously on a previous simulation? So randomization or perturbation types of things. So then where the signaling comes in is when those things happen, it can safely. Well, I mean, signals are considered safety devices, so they would provide safe train separation, so a train wouldn't get too close behind another train, head-ons and stuff like that. So that was part of one of the questions that we had in our thing. And in the end, I mean, as far as the yard itself, for sure, that's not an issue. When you get out on the main line, if we would like to try to have something that we can actually have a little bit of mainline movements on. And again, we're kind of just breaching the subject of how we think we would like to see things. But so far, what I'm seeing is great. So I'm very intrigued with what you have here.
So as far as, I guess, maybe I should talk a little bit about, signaling. Most control of AGVs and trains is kind of directed through these control points, right? So whenever you need to travel somewhere, you say, go to this control point, right? So in this case, what I've done is I have a, at the beginning of the model, I have a list of control points that represent my classification tracks. And then I select from that list an available track, and then I push things onto it, or I push these cars onto that track. The other thing that these control points can do is they can manage allocation. So whenever a train, whenever an AGV needs to move to an AGV or to a control point, it must allocate that control point. If it cannot allocate the control point, then it will stop at the previous control point, right? So,
Okay.
for example, if I have a control point, so say we have some type of a two-way area, and perhaps
well, I mean, if you look at it this way,
see.
one of the things that may happen is if a switch engine or a shunt engine, as you have identified it, is coming in to pick up cars from the opposite direction, will the cars still go over the hump to that track? Because the train, the cars that may be picking up the classed or sorted cars, there may still be, cars rolling down the track. And generally they wouldn't do that, but the point is make sure that it doesn't do that. So
yeah, so let me kind of give you an example, just a very simple allocation example. So say you have kind of two-way a two-way, and this is a very a very thrown together example, right, where you have maybe two tracks converging to one track. And when a train gets here, it will have to allocate to this control point, and if it can't, then it'll stop at this previous control point.
Okay.
Now, and for each one of these control points, you can specify a maximum number of allocations. So in a lot of cases, I don't want this. I don't want to worry about allocations, and so I'll increase this max allocations to like 1,000 or something like that, so that there's no problems but going in there. But if you want some type of mutual exclusion, then yes, you want to maybe have this guy have a max allocation, so that this guy, if a guy coming from here allocates this node, right, then he'll continue on through, and then when this guy comes, he'll allocate ahead, and he won't be able to allocate it, and so he'll have to stop back at this point.
Right.
And then he will, and then this train will continue through, and then once that train has released that control point, he will have to, or at least he'll release it, and then this guy can come through. You can also do it with, there's an object that we have that's like that's what we call a control area, and it represents an entire section. It can represent an entire section of spots, so that if there could be multiple different, it's just a bigger area of mutual exclusion that you can specify. The other thing that you can do is we have triggers on these control points. So I can add a trigger like on pre-arrival. On pre-arrival, which is whenever a train they haven't arrived, but they're at the point where if they were to continue, they would not be able to stop in time to get to that control point in time. And so the on pre-arrival trigger allows you to maybe do some logic just before the train arrives there, and then you can do certain things and say, if I want to stop him, then I can preempt him from his current task, at which point he will slow down to a stop at that control point. Okay. And so you can do there's lots of different flexibility that you can do for like signaling, for kind of semaphore type stuff of like mutual exclusion, where only certain people get in at certain times, and then you can allow other trains
Okay. Well, I mean, what you drew actually is, if you look at it, at the two diverging areas, we call home signals or absolute signals that are, well, they're absolute, so you have to stop. Then the middle would be essentially an intermediate signal. And in our case, what would most of the stuff we would be running on a main line would be centralized traffic control. So as soon as the entrance point, hopefully I'm describing this right, the entrance point would become allocated. Once that is allocated to move through that section, it would actually go beyond the middle point. It would actually carry all the way to the other end, to where the other signals or control points are, and the middle thing is for safe train separation in the same direction, essentially. But the one on the far end, it would, once the one on the, for example, will go left to right, the one on the left, once it's allocated there, we would need it to say, okay, no, you can't, anything at the far end cannot access that track. We don't want the middle one to do it, because we want trains that are following to still be able to follow based on the signal. Opposing traffic, it's called what's APB, which is absolute permissive lock, which is basically it locks down that whole section of track in a single direction. So that's kind of the way it would work. I mean, from what I'm seeing, it's close.
Well, actually, if I were to take this middle one out and just have this control area be here, what this essentially would mean is this guy, when he gets here, he has to allocate all the way to here, and he has to allocate, when he's going there, he has to allocate this control, this entire control area. And so what that essentially means is he would stop here until he is clear to go all the way through to here, right? And then go ahead.
Oh no, what I was going to say was, and in this case, where things start becoming iffy with the signals, and from what you're telling me, I mean, is almost spot on. But for example, if we have two trains that are going in the same direction, it would hold, based on what you were telling me, if we took the middle one out, it would hold the train until the other one is completely clear. Whereas that intermediate signal would prevent, or the intermediate section would allow another train to go in. And basically, in the same direction. So
so that would say the second guy going the same direction would stop, but we also have a mechanism called, in the AGV network, we have a mechanism called accumulation types, where if multiple things are going the same direction on a path, then you have a kind of proximity, a proximity holding mechanism, where it says, you have some proximity distance that you want. So you say trailing edge, from the front AGV trailing edge to the behind AGV leading edge, so essentially the gap between the AGVs, what do I want that stop threshold to be? And by default, it's essentially, I want that to be the target stop spacing. So if I make this like, 100 feet, then what that means is I want the train behind, to go only so far as to be able to stop at least 100 feet behind the guy in front of him when the guy in front of him is stopped. Right?
Okay. So can that be defined? And it sounds to me like this is, and we would call this communications-based signaling, but what I need to do is have a physical location that would do that. For example, if we put something in the middle, that would become the point that would prevent that train from moving forward. And yes, we do have situations where strict distance has an impact. And without going into detailed stuff with signaling, which you may or may not have information on, there are ways that I mean, you can pass certain intermediate signals, you can pass them, you got to stop, and then you move. And then that 100-foot or whatever thing you do, stop it behind a train, that would be good. But he would at least have to, the signal system allows for safe braking to a thing. But in a case like this, from what I'm hearing so far, it would probably be sufficient based on what we needed to do. And that's to, okay, let's go through this, see what the capacity is, and then how long is it taking for the operations to occur? And as we have those things, I think we would probably be in good shape. So so far, from what you're describing to me, sounds like it's doable. It's not exactly the railroad does it, but it's close enough that
and I think where the defaults of FlexSim aren't perfect to what you need, we've provided lots of like trigger, like customization triggers, so that you can and APIs where you can customize it. For example, for another example I was thinking of is you could, on this control area, you could, by default, the control area only allows one allocation, which as you were saying, people going in the same direction, the first guy will get in, the second guy will have to wait, even if they're going in the same direction. You could add a trigger onto this control area to essentially say on request, which is essentially as soon as a train wants to request that guy, you could run some code that essentially says, is this train going the same direction as the train or trains that have already allocated me? And if so, go ahead and let him in, right? And I won't go into that code. I haven't written that code in a while, so I have to look it up exactly how to do it, but you can. So
it sounds similar to the external code that people are using to write stuff with FlexSim, and because I know that the traffic controllers, they do, some of these guys, they because FlexSim doesn't handle something a certain way, they allow a script or something to take care of it. Am I gathering that correct? Is that the way you? Okay.
Yeah, and our main kind of modeling methodology for implementing the logic, we use this is called process flow. So the idea is you actually create a visual diagram of what is happening, what your logic is. So for example, this is my arrivals process. So I have a source where and obviously I think this is faster than real life. Every, on average, 1,000 seconds, but randomly distributed, there's going to be a train that arrives. And then I have this process that I go through. So I create an engine, and then I create the train where I go through and say, this train's going to be this big, and I'm just doing randomness, but you can also read it from a database or something, right?
Okay.
But I'm essentially saying I create a train that's randomly so many cars long, and each car has a certain classification, right? So each one of these is like, I create a car, I set the car's color, I attach that car to the train as an attached trailer. And is this a new classification? Then I add a split point. So I'm actually designating this is a point on the hump, at the hump yard, where I'm going to now split it off, because I have a certain set where there may be the same classification, right? And I have split points where those are the points where on the hump, it would break that train off. So I'm going through and creating a bunch of cars, and I'm creating these split points. And then I say, once I've built my train, then I say, find a receiving track, which is one of these guys over here. And then I travel to the receiving track. And if I reset and run, you'll be able to see that there's these little balls, these little, we call them tokens in here, where you can kind of see it going through. So right now there's an engine that is traveling into the receiving track. And once and then he'll come into this receiving track, and then I put him through an uncouple time, which is, this is the amount of time, some amount of time that it takes to uncouple the engine or do some other stuff. and then I uncouple him from the train right here, and then I leave. So this engine will now leave out to that to the exit, right? And
right.
so you can see here
with your instructions there, like that, for example, and you've got it identified as uncouple, et cetera.
Yeah.
Is that a process? I mean, is there a
Yeah. So
I mean, it has to be tied to something.
Yeah. So each one, so there's different types of, we call these each individual instructions, we call them activities. And there's a set of activities that you can do, which is right here in the library. So, and when you go through training, you'll learn what each of these do. Oftentimes you can learn a subset of like 5 or 10 and figure out, okay, this is what, what I need to do. In this case, like uncoupling the train, what I did was I added in a custom code activity, and then I can put that custom code right in here. And then for that custom code, I can click on the little icon, and it gives me a little drop down where I can specify the parameters of that custom code.
Okay.
And then I click the add button, and then there's a bunch of options that I can choose from. And what I chose was control, and then AGV, and then uncouple train. And in that, so I click on that and I uncouple the train, and it tells me, okay, give me a reference to the AGV, kind of the main head of the train. And that's going to be a certain label on the token that I've set. And then where is the trailer that I want to uncouple at, right? So at which point on the train, if there's, 10 cars, I may want to split at, car 7 or whatever. And so you specify, this is the point at which I want to split off, right? And then there's this other thing, which is a new driver. And usually that's the same as the trailer. So in my uncouple, so I chose that option. And on mine, it was the AGV is my token.engine. So I had a pointer on my, or an attribute on my token that I set that was called engine. And then I said, what's the trailer? And I'm going to say it's the train, which I had a label, which is the front of the very first car in that train I called train. And so I say I want to split at that trailer, and then the new driver, or the new kind of the boss of that train is set to the train as well. So that's kind of, and there's lots of different options that you can do when you add this. So I can, there's all different types of things that you can do. There's some emulation stuff, there's control, you can do stuff for conveyors. There's lots of different AGV type stuff. And I imagine you'd probably be working in here, like redirecting. So you can redirect an AGV. So if it's in the middle of a task and you want to say, no, I want you to go over here instead of over here where you're going, you can say redirect. You can couple a train, uncouple the train. You can attach an individual trailer. So coupling a train can essentially couple on a whole set of trailers, but attached trailers like an individual trailer that you attach on. Detach, recharging, you probably wouldn't do that. That's for battery, kind of AGV battery stuff. There's a train. So there's lots of stuff that you can do. And
maybe they got
go through. As you go through the training, you can kind of learn those options.
Let's say maybe they have a refill diesel refill station at these yards, so maybe they do have quote unquote charging. But Rick, to put it in layman's terms, the thing that Anthony's showing you is what I call a code-free scripting environment. So a lot of the people that go through our training don't know, like, they don't know. Maybe you do know code, like how to program or have some code background, but these little blocks that you stack together are essentially just a set of instructions that a layperson can use that doesn't know how to code. So it's basically a code-free scripting environment that allows you to just essentially put together very specific set of instructions on, you know, how a train, or, you know, how it would operate. But it allows for ultimate flexibility.
Right. And to be fair, and I used to be a coder years ago, but not anymore. But for example, my RTC software, and this is a question that you know, I guess I'll go ahead and ask it now. A lot of what is done is we have it's set up with links and nodes. That's the base of the entire the physical infrastructure, and each link has parameters: speed, is it curve, is it on a grade, and the individual nodes are points of change between. So if you change from 50 miles an hour to 40 miles an hour, then you have a change point. You have to put in, there's a node that has to be there that effectively changes the point. And so I'm not really coding when I'm doing this. I'm applying parameters to each individual things. And then everything is driven by a timetable. And that's where I was going before. Can we, and my assumption is, and I hope, is that we can schedule certain activities, particularly when a train arrives. For example, and I'll, when we get a little bit further, if you guys are interested, I'll show you how RTC works to give you an idea of where my basis is coming from, and that's where, so my questions are based on that. RTC will not individual train movements, which is the reason, you know, an OpenTrack won't either. So that's kind of why we started looking at trying to evaluate some of this stuff, is because we need something that can take it and go above and beyond outside of what we're doing, and without having to do a lot of true coding per se. So what you're telling me is a good thing. Like I said, I don't really code in RTC. I provide parameters to certain infrastructure, and the trains are run based on physics. And then there's a smart dispatching system that's been developed by the manufacturer that uses a priority code thing to tell what trains when, and of course the signaling system in there. And I can show you that if you're interested. If not, it's not a big deal. But there's where we're kind of driving at. We need something that will go by a time schedule, something we can do perturbations with, something that's going to have a wide variety of you know, lengths of trains, different types of cars. And my guess is that these control points, and when you assign it as a processor, you know, type of thing, that the processor is the one that's making the decision to route the cars to the individual tracks they go. Okay. So I need to make sure that I'm following with what it is, and I'm trying to make kind of comparisons to a piece of software I use, which is, it's not really fair because they're not really on the same level. They're similar, but they're different.
So yeah, all of this stuff that I built, you can build on your own, mainly by just entering various values, by putting these activities in and entering certain values. There are some like expressions that you might write, like if this equals this, then do something, you know, some basic expressions. But for the most part, you just, you put these activities in, and that becomes the logic of your simulation. And you can also do, so we have this idea of a schedule source, and this is probably what you do for an arrival schedule. And the idea is you're gonna have, if I look at this, you can have a set of times that trains arrive, right? And that, and you can specify, you know, 1, 2, 3, 4, right? And you can also import this from Excel, right? And so there's lots of options as to how you can get your data in there, and then you can run this as a schedule set. And what happens then is, in the simulation at a scheduled time, one of these green balls will pop out, and then you can do your logic as to how, you know, what type of train is this thing arriving, and how do I build that train in FlexSim based upon the data that I'm reading from whatever database or Excel sheet that I'm getting. And then you would, you know, build that train, and then you just run it through whatever process you built, right?
Okay. Yeah, I mean, so that's fine. Now, interestingly, although we use arrival times in the simulation, our stuff is more departure times, and we allow the physics and the interaction in the network, our train performance calculator, and then we have a series of things that even though we can specify an arrival time, and essentially what that does is give us if the train's later or early or on time. But all our stuff is driven from the time it departs to when it gets there. But this would, I'm pretty sure this would be fine. That if we had a rough idea of when the train, essentially what we would need is, okay, we have X amount of trains and they will arrive at the yard at this given time, but we need to be able to have some perturbations in it where it may come 20 minutes later, may come a half hour, or may come early. Those kinds of things are where, you know, when it comes to the timetable that we have an interest in, because we need to make sure that, you know, as you probably know, a simulation that has no perturbations in it is
not quite as useful.
Right. So we need to make sure that, and unfortunately, as you probably are aware, trains are notoriously all over the place when it comes to time.
Yeah, so, but Anthony, can't you put instead of like an arrival time, can't you put a stochastic expression in there, like a random?
Yeah.
So like
you could put an arrival time, or you can say I arrive, and then I say I add a random delay after it arrives that represents the amount of time on average that it's late, right?
Or early, yeah.
Right. So you know, this token would arrive at the exact time of the scheduled arrival, but then you can impose some random delay based upon, you know, whatever, you know, on average they're 3 minutes late, but every once in a while they're an hour late, right?
Right.
And so you can impose a random delay in addition to that scheduled arrival, right?
Okay. Yeah, I mean, that's fine. The one thing that we want to make sure that we don't do is if the train arrives, and then we put a dwell on it, that it's not preventing another train that may have arrived on time to actually do their function.
That would be part of your process, like part of how you build your process. Do you delay before you start acquiring things in the model, or do you delay after you've acquired things? And if you delay before you acquire things, then it doesn't, you know, it's just a little green ball that's waiting for a certain amount of time. But if you arrive and then you start acquiring stuff in your model, and then you do the random delay, then everything else would have to wait. So that's just based upon how you would build your process.
Yeah. So you'd want them to delay in the ether and then wait to obtain a track after they delay in the ether, right?
Yeah, I mean, essentially, yeah. I mean, there's a wide variety of ways that these things happen. So, I mean, there's a potential, and it may be to the point where, you know, we just need to get a series of simulations, come to a bell curve, you know, make a bell curve out of it, and just do individual simulations with varying, you know, even if we have to do it manually, varying the times that the trains arrive at the
well, and Rick, so, we have an empirical function that allows you to just grab the last month of arrivals, put it in an Excel spreadsheet, and let that build your delay for you, right? You could even tie it to an almanac, for heaven's sakes. If you have a weather almanac, you say, well, when the northeastern region, when we have storms, this is what typical arrival stochastic looks like. It's broader, right? I mean, these are all things. Everything's data and table driven within FlexSim. So you can build permutations of it to, you know, till you're blue in the face, because you can, you know, build certain reference tables and make it behave differently. But it is interesting. It's an interesting thing that you've a challenge you've got to build these. The other thing too, Anthony, I had a question. I'm sorry, I don't want to commandeer because this is more primarily for Rick. But you have the paths and the nodes have like speeds and accelerations and decelerations, etc. And then you actually have AGVs and trains that are on top of the paths and nodes. And is one master to another, or do you understand what I'm saying? So like the train itself, does it have a maximum speed, but it's throttled by the track that it's on?
Yeah, well, it's all based upon this table here, right? It's essentially looking up in this table the cell that applies, right?
Oh, okay,
So
gotcha.
it's both based upon the path that you're on. It's based upon the type of AGV or train that it is, because you can have different types of AGV. So if I have different trains on the same track and with the same load, you could have different speeds. So each one of these has its own set, right? So you
Okay.
can split it out by path, by AGV or train type, and by what we call load type, which, generally the idea would be, what is on that train, but
Yeah.
you could really have it be anything. What state is that train currently in? And based upon that, it looks up which AGV type it is, it looks up which load type it is, and then looks up which path it's on.
Right. And so if it had 100 cars with 2 engines, and obviously there's an electricity demand for that it can generate for the diesel electric engines provide so much electricity and they powers the individual wheels. So if there's like if you had a table of like, 10 cars or 20 cars or 40 cars or 80 cars or 100 cars, then you can actually build a reference table of speeds based on essentially how many cars and loads.
So usually, I guess for a given train, it treats the train as a single entity. And so you would want to have the train have a certain AGV type, right? Based upon, and then if it's a longer train, then maybe you would have a different load type, a long train load type, for that train. You know what I mean?
Yeah,
So.
gotcha. Okay.
So, I mean, to carry that further, and maybe it's the same thing. For example, when we have let's say we have a train that's got X amount of cars in it, or X amount of different types of cars in it, and there are, for example, an empty bulkhead flat car. In most railroads, an empty bulkhead flat car is limited to 45 miles an hour, but the rest of the train may be good for 60. And of course, car in there, that limits the speed of the train an hour. So I'm wondering, so if we, based on this, if we put the car type in there and then we put a speed in there, and if that speed is lower than the other speeds, what will the, and see, this is where obviously the simulation, the hump simulation here is kind of exactly what I was imagining it doing. But if we have a train approaching, and to be honest with you, at this point, we haven't developed, how far out we want to do something or do it. But if I have a train that has one car and it's 45 mile an hour limited, it's going to go 45 instead of 60. So that has an impact on it. And so taking it a step further, if we have a train that's being randomly generated, like you were talking about before, and it generates one of these cars, is it going to take into account that, okay, I got a 45 mile an hour car in here?
So the way that you would do it is, the way that I would do it, I'm sure there's different ways you could do it. I think the way that I would do it there is maybe I would add a load type that is I'd call speed limited. And what that means is, for this, if a given train, if I have attached a train or a car to that train that is speed limited, then I want to be in this load type, right?
Right.
And so what I would do is when I attach that car to that train, I'm going to store a value on the train saying, hey, you are speed limited, right? And there's different ways that I could do it. I could have it be a Boolean, which is a 1-0, or I could have it maybe be an array of references to all of the speed limited cars that he is currently attached to. And then so it's the thing that sets the load type is this initialized travel. It's like a trigger that happens at the beginning of the task. And then in here, I would say I would probably have a and this is code, but it would be a little bit of code where you would write something like, if TE dot is speed limited, right? So I would have set a label on him called is speed limited, and then I would say then load type equals 3, which is the third column here, right? And then I would say else, otherwise load type equals something here, right?
Okay, so and basically what you're saying is that if this particular type of vehicle is within the train, then the entire train's load type is reduced.
Yep. Yeah.
Okay.
Yeah. So whenever I attach something, I set a label that I call is speed limited on that train. And then whenever I start a travel task, right, it will check, hey, do you have this value? And so I need to make sure that when I detach those guys from the train, that I would say, okay, now you don't have anything speed limited, so set it back to 0. And so then it will, do nothing here, or at least
Right.
it'll do the standard, right?
Well, hopefully none of the detaching will occur outside of the yard activity itself, because I don't think our intent is to
Oh, yeah, I guess that's true.
model outside the yard area. So once it gets in the yard, it doesn't matter. I just want to make sure that the train is cognizant of the fact that there is a speed limited vehicle within the consist.
Yeah. And you can do that.
Okay, good.
Yeah.
Okay. So far, so good. This is pretty interesting. I mean, I keep in my mind, I keep looking at how it compares to the way I have to do things in the software that I have. So it's a very interesting process here. I guess the key thing for me is to understand the individual items that you use as sources to make sure that they're appropriate for their, and it sounds like this AGV thing is probably takes care of some of that for me. So that's good.
Yeah.
Because for example, and I guess so let's say we and this is a simplified back and forth movement. So we had the train come in, and to be honest with you, just to give you an example, our arrival and departure, the engine would be on the right side of the train. He would pull in, he would cut off, he would a hump yard, or he would back into another track that's there. So he'd be on the other end. Then the switch engine or the hump yard engines set would come in, and then he would shove them back over the hump like you have. But where was I driving with this? But then once we get in there, obviously it doesn't matter. The speeds would probably be all consistent, because on a hump yard we have retarders. So once the train goes over the hump, they've got a series of retarders that will keep the train, and it looks at it by the weight of the cars and stuff, and it'll retard the cars regardless of their type at this point. Will retard the cars to a given amount of speed, because they can't go. Standard coupling speed is not exceeding 4 miles an hour. So we don't want anything to go over 4 miles an hour. So if we have a 100-ton car, and then you got a 30-ton car or whatever, they essentially need to approach the cars they're coupling into at the same speed. And so, I'm not sure how that would, I kind of got an idea how that will work, but it probably doesn't matter in the end, as long as we make sure that the speed is consistent coming out of the starter.
As a gun enthusiast, where I look at a 220 grain bullet traveling at 1,200 feet per second, I ask myself, is there more foot-pounds of energy with a 2-ton train traveling at 4 miles an hour than there is at 220 grain slug at anyway, sorry, that was a tangent.
No,
that's a lot of energy at 4 miles an hour. That's a lot of energy.
Yes, it is. But and the interesting thing is, most of the time, I believe, and it's ironic that you set it up that way, and I don't know if you did it, but usually 3 or 4 cars is the limit that will be allowed through the hump controller at a given time.
At a given time, yeah.
So like when it.
The reason I did it was because the distance from here to here was 3 cars, and I didn't want to go any further because this is the point where they, like, the lead car travels to, and it's like you split off at this point. And so I was just like, oh, well, I need it at that point. I need these end cars to not be going off past this point, because if they go off past this point and then I need to send them over here, then I've already gone too far.
Right,
That was the reason I did it. It was just for geometry's sake.
Well, the interesting thing too is you know, you had some concern that the trains actually stop at the control point.
Yeah.
That may not necessarily be an issue, because as long as we account for the time that
Do the extra, account for that extra time. Yeah.
Right. So then, you know, you know, there's ways of working around it. The motion and the overall time and how we're moving trains in and out based on, you know, getting capacity, how many hump yard engines do we need? I mean, there's a lot of variations the way we could simulate. I mean, we'll do what ifs. We'll just see what the capacity actually is. You know, there's all sorts of different ways of how we want to do it. So the best, you know, for me, the thing is that we can do it in a consistent manner. And as long as it's consistent, you know, there's not, then I think, so if we have to stop at a control point or whatever, I mean, so be it, as long as it's for, in the actual, you know, in the end time. Yeah. So I mean, so far, I'm seeing what I like. I mean, I like what I'm seeing. I should put it that way.
Yeah, looks like I may have messed something up. Oh yeah, I put that in. I need to open this up again. But yeah. So that's kind of, I guess, that's kind of all I had to show. Are there other things specific questions you had about it?